which has been an ongoing project for many years, and this is the second time giving this talk here. So where we're at. So the thing about this project is it's one of these projects that won't die. So it's one of the oldest projects around. It's over 8 years old. Mainly it's been going on for that long because it has gone through stages of progress and stages of languish where we didn't have much going on. So, and for example, one of the points was it was upstream. It got removed from upstream because they viewed it as lack of involvement because there was only at that time it was just me. Also, it was initially pushed to the staging tree, which was the wrong fit. So in the Linux kernel, the staging tree is this ground where your driver is pretty much ready, and it's just there to go through the final stages of cleaning and meeting the Linux kernel standards, and then it's integrated. But Lustre is like one of these active projects where you have thousands of lines of code changing every week. So it's not really a great fit. So after it was removed, we had discussions with Neil Brown and with the VFS guys, and we said, well, it's better just to put it in the FS directory with all the other file systems in the next go around. So, and also it's just limited resources and limited support for this project. So as we know, it's very expensive to, when we were talking about Ubuntu, and I was describing how much is needed to do testing. You don't realize there's hundreds of VMs. It's a huge process to do tests. We have thousands, tens of thousands of tests done for every patch. So as patches come in, you multiply that and you run into millions of tests being executed at any moment in a test rig. So you need a huge structure to do this kind of testing. And because of that, and then you amplify that by LDiskFS and ZFS, those matrices and all these distros, and it just it spirals out of control, and then versions. So because of that, everybody in the communities focuses on different tests. Like ARM does their own testing infrastructure. Ubuntu is done by the community, various volunteers, and then of course WhamCloud focuses on Rails support. But the good news is, though, even with all the limited resources, there's been always community involvement, and it's kept this project alive. So over the years, Oleg from WhamCloud kept it alive for several years. Myself kept it alive. There have been various, over time, people revolving in and out who have contributed to the project. Like Arleon from Amazon contributed a little bit, and also Sean Tushav from HPE, he did a lot of work for kernel and support for newer versions. So it's been a good project, and then of course Neil has been involved with it for several years. Also the good news is that we've been really close to completing this project now. So we've synced it to the OpenSF tree. It's been like that for well over a year now. So everything, all the functionality you see in the latest master is actually in the native client tree that exists. The goal is to actually submit this back up to Linus when IP version 6 work is done, which will be at the conclusion of 2.16 development cycle. So we're looking by the time of the next slug, this is going to be pushed to Linus, and we're going to see what the community feedback is, and then go through that process to merge it upstream. So where have we been over this last year? So of course, like I said, we've been in sync with master, and it's been kept in sync to this day. We have finished the flow now that the native client is equivalent to the OpenSFS. We've had this flow of a lot of work that was done on the native client that was independent of this from the Linux community when it was in the staging tree. So we've been going through that. The good thing is that a lot of the development for newer kernels is done there first, and then it's backported to the OpenSFS branch. That also means things like any OFED changes, because OFED is always tracking the latest thing, we end up encountering that before the OpenFSS branch, and then we can backport that for them. And the other benefit is, of course, support for new distros. So like in this last development cycle, we were ready before Ubuntu 22 and RHEL 9 was out. We just had support for this stuff. We were already developing, and it was all landed. So it was just, as soon as it came there, it was ready for broader testing. We also saw various performance gains. So there was some work like during the 2.13 cycle, and like we found like our hash table implementation performs way better than the libcfs hash table implementation. So we get all these performance gains. We broke up various locks and the complexity of the LU object handling. So there was all these nice little pro benefits to it. As it currently stands, we're at a 5.9 kernel. And I have a patch that I'm developing to get up to 5.15 for the native client. So that patch is still in the work. So the biggest complexity right now is the way Lustre handles its embedded fscrypt and the native crypt. They've reworked fscrypt several times. So, and right now one of the biggest changes is because fscrypt for the 5.4 version up to 5.10 didn't properly support, if you know memory allocation, there's a special flag called GPF no FS. That's not properly supported by fscrypt. So they had to go and rearrange how they allocate it and built a file system encryption context. And it's quite a bit of work, so I've tried to do that, and I'm piecing out those bits. And as I pointed out right now, it's so once that's resolved, we'll jump to 5.15, and then Sean from HPE has been working on even newer kernels, so there's patches for that. So I can go and test those as soon as I'm done with the fscrypt stuff. And as I pointed out, it has been a great community effort. Neil Brown from SUSE has been doing a great job. He's been driving a lot of the IP version 6, and of course myself. And I also have been working on the IP version 6 with that. And of course there are many others who have come and gone, and I'd like to thank those people who've contributed to this project. So how healthy is this native client? So we do the same testing as like ARM and Ubuntu, so that's usually covers LNet self-test and sanity testing for light testing. And of course I actually do heavier testing locally, and so I've been testing any of the config sanity and stuff, and I find that it's pretty much comparable to what we have. It's pretty much the same bugs in both trees. There's a couple exceptions, but mostly for the most part. Now the nice thing is within the last 12 months, we've made it so that the OpenFS tree utilities, Lustre, you can actually build the utilities to work with the native client. It just works out of the box. So if you do configure and you disable Cerber, you have an option called disable modules. And when you do that, it just builds the utilities for you, and you can just install it with the native client and it works. It's that easy now. And with this, we can now do automatic testing. So as we saw over the last 6 months, ARM has been working on doing this, and we gave a presentation at LUG about this. And I've been following and talking with ARM how they're doing this, so this way for the native client support we can move to this kind of testing ourselves. We just have to work out a test system, and at ORNL we've been discussing about using like a cloud service provider to build our own testing rig to do this. And so probably the biggest bugs that we see in testing is the FID lookup cache. So that's been a complex bug that's actually more difficult to solve than you think. And the fhandle stuff is not quite correct in its behavior currently in the Lustre code. So I've been trying to figure out how to fix that, but it's a touchy one. And I haven't had the time to do that because I've been focusing on other issues. And over time, we've been resolving any bugs that have handled. The most common thing that does happen is occasionally, because we don't do a test build with the OpenSFS tree against the native client, occasionally we get UAPI breakage. So this is the userland header stuff. So occasionally something will leak in and it doesn't quite, it'll do some kind of build breakage. It's not often. Like the most recent one, which is going to land very shortly, is that HPE landed their support for their new LND driver. the K-Fabric stuff. And of course, we don't support that upstream. That's, there's a lot of licensing issues to support that upstream, and that it's not in the native kernel, so it doesn't build. So I had to make a patch that says, well, okay, we don't support this driver. So what are the final touches? So there is a big ticket to cover all this. This is LU 12511. It tracks all the work, and you'll see there's like 50 open subtasks. Most of those are closed, so actually. There's a couple big items left. The largest is being the IP version 6 work. A good chunk of that was done during 2.15, actually. If you look in the code, a lot of the infrastructure was landed. It's just a lot of the outward interfaces and the wire protocol wasn't done at that time. The IB support, as Andreas pointed out, that needs to be resolved during this time. So one of the things is our InfiniBand driver is extremely large. It does a lot of its own handling. So in newer kernels, for when they did the OPA drivers, they required that they would do a generic RDMA API, and a lot of those drivers have been moved over to that API to make the driver much smaller. So they requested that we would do the same thing. They would like to see our InfiniBand driver to be only about 500 lines of code instead of, the 5,000 that we have right now. And of course, we keep, as testing expands and as we keep moving forward and these newer features land, we keep testing to make sure. And one of the unique things about it, much like ARM, there are strange bugs that are found only on the native client that you'll never see. There are things I can reproduce. Sometimes one client will say, oh, we have this bug, but we hit it in 1 in 100 runs. And I'm like, I can see it every single time with the native client. And that's because there's some timing issues because we don't have all the debugging infrastructure that the native client relies more on the debugging features that the kernel natively provides instead of the special debugging features that the OpenSFS tree does. And because of that, that changes the timing mechanisms of a lot of the debugging code, and that exposes us new types of bugs. So what are the biggest bugs left? So one of the biggest changes is actually the proc handling. So in the Linux kernel, everything's being moved out of proc now and being moved to sysfs and debugfs. So that was a big change. So the native client already has everything moved over to these things. Where OpenSFS, we've been gradually moving it over because there's some side effects of moving it over to these trees. So one of the biggest side effects is the debugfs system. It's considered not a safe area to use, so it's not generally allowed to use to non-root users. And so that broke things like lcuddledl and the stat stuff in the upstream client. So when we came across that problem, one of the inspirations to solve that problem was something that I discovered that the Android phones actually encountered. So Android at one time, how your proc tree, you could actually look up the statistics of of all your applications. You could look up your task IDs and stuff like that. So Android phones used to do that and scan the entire proc tree, and they found that it would drain the battery in less than an hour doing that. So they realized that they needed another solution that was less CPU intensive. So they actually developed something called TaskStats, which is a Netlink API, and they found that the performance was many-fold times better. So actually, we are looking to replace a lot of the debugfs stats with a Netlink YAML API, which Monday with the developers, I presented how to do that. So this is actually going to give a huge performance win. Instead of opening thousands of proc files to get your stats, you'll only have to open a single Netlink socket, and it'll download these YAML data structures for you, so you can parse them and do whatever you want, and it interfaces with Python. There's all these benefits with that. The other issue is that the sysfs has strange naming conventions. So when you look after you mount with your, when you do your lcd get params, you see this long number string. Well, technically that's a security violation because that's actually exposing an address pointer in the kernel space, and that's considered, it's called ASLR, and it's considered a big no-no. So we need to change that. So we discussed about changing it to new fields, and our tests are ready actually for those changes. And so those are the changes for that. The other one is moving to R hash tables and X-arrays to replace the libcfs hash table implementation. And of course, as I just pointed out, the ASLR compliance. We've reworked the mount code. So one of the changes you're going to see is that mounting servers and mounting clients is slightly different. Currently, you can mount them as a type Lustre, but there's a new type of mounting configuration for servers. And there's a reason for that. And of course, the FID lookup and fhandle fixes that need to be done. So what are the visible benefits that you can already see in 2.15? There are some benefits that came out of this work. So every changes that we do, I look to see what can improve the life of the user. So one of the things with sysfs is you can do UDEV rules now. So like our Frontier system, this is one of our rules that we put in place. So we can auto-configure as soon as the modules come up, and we can run our own scripts. So instead of just doing your classic lcutl set param, we can do all this elaborate work. Also out of that, we can do client eviction reporting. So there is actually some work being done on that. I want to land that for 2.16. So when your clients can get evicted, it will actually send you a UDEV event. So you can actually write scripts to log that this client's done, or you could actually try to reboot your client. This can be all automated. So as your systems fail, you can actually try to like resuscitate them. I like to call it the CPR system. So, and the other plan is actually to do this also with LNet HealthNet events. Right now we have health events and it takes it down, but there's no notification of like when LNet has a hiccup. You find out after users start complaining that their applications are sick. This would allow you to actually know as soon as something is going wrong. You would be notified. You could end up having scripts. You could end up automating a system that tries to recover as soon as these events happen before you find out from the user. Other benefits is we want to unify the the sysfs naming space with UUIDs. So, you know, in your traditional file systems, you can mount it by a UUID, which is consistent across reboots. Currently, you don't do that now. Currently, sysfs with our UIDs, they're unique to each node. So it would be nice to have that consistent around there. So your each mount instant would be consistent every time you mount it. You could write scripts and you would know, oh, this is my UUID for this mount. So you don't have to do just star. You can actually use the proper UUIDs. The mount targets have changed for the servers. So there's now a mount-t Lustre target. It's not just Lustre. And the reason for that is that we're inverting the way the structure works for the mounting code. So currently when you start Lustre, the LNet layer comes up, the portal RPs come up, and then mounting happens. Work has been done to reverse that, so the LNet layer doesn't start up instantaneously. It is only on mounting that the LNet layer comes up, and then it starts to do the protocol. And there are some reasons for some benefits to that, because like one of the issues we've had in the past and we've seen is that you have all this network traffic coming, and then when you try to on-mount, it kind of can't on-mount because the traffic is still coming. So in this case, when you go to on-mount, it tries to drain the queue then. It's a different order for that. And of course, there's work that's going to be done on fhandle. We're going to properly support that API. Same with file sets. That's been broken for a long time, and ORNL's wanted that for security enclaves. We're looking at GenRadiX trees for allocating large data sets. So one of the issues that we've seen, and this is a new API that was developed in later 5 kernels. And so one of the issues we've seen is that vmalloc will tank performance for large data sets that are allocated constantly. And of course, the last thing that we're going to do is the migration of stats handling to Netlink. So with Netlink, there's a huge amount of benefits over the current methods of gathering stats. And then down the road, there will be the ability to configure your stats to only report stat fields you want. There's a lot of opportunity there. So probably the biggest changes, and probably the one that's of most interest to people, is the LNet changes. So we're going to see IB version 6 support, and not only IB version 6 support, but also IB hardware addressing support. So you'll be able, that's a 20-bit address, so you will no longer need to set up a TCP stack on your IB. You'll be able just to talk to the remote hardware addresses. We've gotten to the point where, as you can see, we can actually bring up IB version 6. Last week, we're just getting that. We're trying the ping code. The ping code I found has some issues because it has not been tested before, but now we're getting testing, so we're working out the bugs for that. And then from there, it'll be easy to send the protocols for the data itself. The other thing is this new IB version 6. So there are roughly 60 ioctls that are used for LNet. Some of them are non-multi-rail and some of them are multi-rail. And with IP version 6, that means that we would have to double all the ioctls and rewrite them. So what I did is that's why we're using the Netlink API with YAML. So that gives us the benefit to replace all those ioctls and use one API for everything. So it's completely backwards compatible. The other nice thing about that feature is that the API can change all the time. I've written it so that the API is backwards compatible indefinitely. So if you want to add a new feature, it won't break the old tools. And if you are running a new tool with an older kernel, it won't break. You just can't break it. I made it pretty resilient for that. And of course, LNet self-test is the same way. So I am not a fan of the current LNet self-test. I found ways to crash my nodes with it in so many fun ways. And one of the things that I hate is the scripting interface. So it's going to be YAML based. You will be able to create YAML configs and feed it to LNet self-test. No more typing in every single line to execute it. We will still support that, but in the background, it'll be creating the YAML file for you to send up at the end. And another nice feature will be using LNet Discovery for mounting. So theoretically, you won't have to set up LNet. When you go to mount, it'll use Discovery and it'll scan your network interfaces and bring it up for you. So the days of setting up and configuring your LNet and then mounting, they could be over for you. So that's probably going to be a huge benefit. The only thing you'll have to do is do blacklist to make sure that interfaces you don't want to do don't come up. So those are the things that are going to be looking forward once 2.16 is done. So what does the future hold once all this work is done? So once it's merged, you're going to see it in distros. So, and who's going to support this? Well, of course, SUSE is involved in this work, and SUSE is concentrating. So when they go to do their test rigs and do full support for Lustre, they've decided they only want to do the native client. They don't want to do the OpenSFS tree. They'll be going immediately to that. And as for Ubuntu, that's the closest to upstream, and there's heavy demand, and even from the last discussion, we see that there is a large interest in the community to support this. So Ubuntu will probably be still a community-supported effort. We'll have to figure out how to, once we figure out how to do an external tree, we're going to have those bugs reported to WAM Cloud like ARM is trying to do. And of course, one of the biggest benefits of this is to get new developers into the community. So this is a big thing. And of course, the other thing, one of the other big benefits is Lustre does tend to develop new things, like Sebastian did FSCrypt, the performance gain. So I did submit that to them, and they currently said, we're not interested in it because there's no real users. When Lustre gets merged, we'll consider it then. So when we get merged, they will get this work. And then in the future, whatever we want, there's a bargaining tool for this. Then, of course, this is the last time I'll probably be discussing the client work here. The next step will, of course, be moving the rest of the tree to the upstream kernel. So that means no more LDiskFS patching. I know there's probably hand claps for that, especially on the Ubuntu people. So that we'll be able to get LDiskFS and ext4 will merge. And of course, everything that we're doing in the OpenStack tree to support the native client is already being done, so it's a very small step. It's not going to be a multi-year process. We're talking probably a year to move the rest up. And then, of course, there's always the welcoming of community involvement in this project. So as we gladly welcome anyone who would participate. Like before, we have rotating support. As we prepared for the merger in the 2016 timeframe. So we're looking by April or May to submit this upstream. And of course, we need greater scope of testing. And there's the URL for where to grab the latest tree. And there's information how to test it. And of course, welcome to Open Bugs if you test it. I know Nate Ruttman from HPE tests the native client. He's shown an interest. And of course, you can ask questions on the Lustre Develop mailing list. Or the LWG, we always discuss it at our calls. Or you can discuss it at these Lustre conferences. And then in inclusion, we're pretty much close to done. This is my last SLAD talk on the client stuff. And of course, don't be afraid to ask questions, join calls, mailing list, report issues, or you can contact me directly about this project. And I would like to acknowledge Oak Ridge for the support of this project. Without the support, this project would have probably died many, many years ago. Thank you.
Thank you. Any questions for James? What's the status in upstream versions? I mean, Red Hat 8 and future Red Hat 9?
So you mean like what will be the next version, distro versions will support?
So today, using Red Hat 8, what's the current
So
status?
I do testing for my system. I have a modified RHEL 8 and a Ubuntu 22 system running those kernels. I run the native client on that. For the reason is Ubuntu 22 supports FSCrypt natively. RHEL 8 doesn't. You have to like build your own. But yeah, I've been running modified kernels on those.
And for upstream, to have it upstream on non-modified systems, is this planned or is it for a future version?
It'll be for a future version. So to merge it, we're going to have to sync up to the very latest wherever Linus is at and then merge it during those merge windows. So we're looking probably somewhere around 6.2, 6.3 kernel.
Any other question? No one? Online? No question? Okay. Thank you, James.
No.
Thank you. So, change the subject totally. First of all, my co-presenter couldn't be here because he's neck deep in solving different problems at Oak Ridge, which is due to Oak Ridge. I think I paraphrased James when he says, they love our hardware, but they don't like our software. So yeah, exactly what he meant for that, I don't actually know, but obviously they have their own stack and they want to implement that and so on and so forth. This creates a little bit of a problem because it's a combination of our software. Anyway, John isn't here. He's also the guy who spends most of his waking time doing these benchmarks that I'm now taking credit for. I used to do benchmark way back when, but honestly, I can't be bothered anymore because benchmarking is difficult. Benchmarking is hard, but it's also boring if you have issues because you have to rerun certain things over and over again trying to figure out why things doesn't work. So I do want to talk a little about benchmarking, especially why we're doing the benchmarking all the time. And we actually run benchmarking daily, and sometimes several times daily, depending on where we are in the process. Now, the biggest challenge we have is the fact that hardware keeps changing. Hardware keeps updating, which is good. But it also means you get new versions of ways of doing things. You get new architectures, you get new kernel versions, you get new network types, you get new tunables, and so on and so forth. So if you kind of look at some of the complexity we have here on the hardware, I mean, moving from an Intel platform, which we did earlier, to an AMD Rome platform, it was kind of no-brainer, right? You go from something with PCI Gen 3, limited amount of lanes, to PCI Gen 4, 128 lanes per CPU. Great. Unfortunately, these chips are multi-chip assemblies, which means you have a NUMA processor in there that needs to be handled differently. And different file systems, or different versions of the file system, which say benefits from different ways of doing that tuning. So we actually have to go through every single step of the chain from the client side, over the network, to the servers, to the drives, and everything in between to find the right tunables at any given time to be able to kind of get the right performance out of these systems. And with right performance, I mean the best performance. Now, the second part of that is that as we go on, as we iterate on and on, we need to make sure that we can maintain that performance. Because one of the things that may be debated, but one of the things we found that every time we have a new update to Lustre, every time we have a new client, every time there comes a new patch, the likelihood of actually having a performance regression is greater than, not having one. So we keep finding issues where those performance regressions need to be addressed to keep pushing the envelope of these systems. And the reason for that is not that we are that picky about a percentage here or a percentage there. But the worst question you can get if you are an architect like myself or support or what have you in a company is the fact that you have your customers calling you and saying, the file system is getting slower. That last update you did wrecked our performance. We can no longer hit the peak performances. Now, that's sometimes subjective and not actually real value, but proving that is really hard. Anyway, I want to go through a little bit about some of the things we've done over the last couple of years and some of the results we have, just to give you an idea where we are currently. Now, the benchmarking is really also one of these things. Why do we do benchmarking? It's because we need marketing numbers. Well, marketing numbers can be made up, and most people make them up any which way, so it doesn't really matter. So it's all about how can we get specific results. Now, the customer benchmarking, when a customer comes to you with a set of requirements, those are, I wouldn't say easy, but they're well defined. You know how to do it, and you know how to get the best results, and you can do that consistently. But when you have a product that evolves over time, you get new firmware and so on and so forth, maintaining that and proving that you can maintain that with different tunables is really the main reason we're doing all these things. Now, what are the technologies to use? We have IO500. IO500 is supposed to be, oops, that was actually one too many. Well, it's funny. It has a life of its own. IO500 is supposed to be kind of the top 500 of storage. I was actually involved in the creation of the first IO500 way back, but I kind of split from the team because we couldn't agree on the hows. And one of the problems I see with IO500 is the fact that it's not limited to production systems the way it is in top 500. That means you can create a Frankenstein system that can get some fantastic results, but has absolutely no validity in real world. And that kind of makes the whole process default. That's why you won't see any HP systems on that list, despite the fact that we could score high on some of them. Some of our customers have made their systems available on the i500, but we are taking a stance against that because we don't believe that's the right way. You also have the problem that you have some of these tests, like the 10-node cluster. Well, we can't saturate our storage with 10 client nodes, no matter what we do. We need more. So it will also always show some of the stuff we do in a bad light. So we're going kind of old school. We're taking the latest versions of IR, the latest versions of MD-Test, the latest version of FIO. Sometimes we do IO-Zone as well. And we use the settings that we can. In some cases, we actually modify to be able to scale to the right size. I mean, D&E and being able to scale MD-Test to 20, 30, 40 MDTs have been a challenge, just to put it very lightly. So all of these things we do, but we also try to be consistent over time. And that is really the biggest challenge we have in where we're going with the, kind of these things. And again, the challenge is consistency. Now, our test environment is not the greatest. We don't have unlimited nodes. We don't have unlimited systems. All our systems is essentially about 20, 21 nodes of PCI Gen 4 based clients using whatever network is supported at any given time. And the networking part is actually a different issue as well, because we currently support 3 different types of networks with 4 different types of settings. And that being obviously InfiniBand, which everybody kind of knows well and know how to optimize. It is Ethernet running on Mellanox hardware with either RoCE or TCP. And you might wonder why we do TCP at all, but that has its uses. And then obviously we have the Slingshot, that is our own version of the Ethernet fabric that has totally different ways of working, despite the fact that it is Ethernet. And all of these things need to be done for every single version of the code we do. And that's also part of the challenge. And it really comes down to how can we show that the numbers are consistent over time. Now, we've also done a lot of work with software RoCE, where you actually are running a hardware RoCE on a Mellanox NIC in Ethernet, and then you'd run the RoCE on the clients in software. And that's the reason why we had to do that, because some of the protocols we use doesn't have all the bells and whistles that it needs to be at any given time. And we now can show that actually software RoCE can match hardware RoCE, despite the fact that we use about 5% of the CPU capacity to get there. So it is not pain-free, but it can be done. And that's kind of where we are at the moment. Now, our test rig, apart from the clients, which are fairly standard, is based around the latest generation of our hardware. And it's really, not that unique type of hardware. The nodes we're using is actually dual node systems, each with an AMD Rome CPU, sharing the drives, whether we're using that for our management unit, for our metadata units, or for our disk server units. And the disk units we use are your standard Seagate 106 drive enclosures, the same as everybody else is using pretty much in the industry today, the highest density you can get from a disk drive. So that's kind of our building blocks. Over the years, we've had a number of releases of our software stack, and I've picked 3 here, which is the Neo 4.1, which was the one that debuted with the Cluster solution back in 2000, essentially when we started bringing that to market. The 4.4, which was the latest, I would call it, main release of that one. We actually have 4.5 out now, but it's more for fixes and other things. And the 6.1, which is where we went to Lustre 2.15 and a newer kernel. Now, that seems like an easy thing to do, moving up to a new kernel and at the same time moving up to a new Lustre, but tell me that's been painful. Not just because Lustre have been, actually, late, Lustre 2.15. I mean, we expected it in December last year, and then it got moved to January, and then to February, and so on and so forth. For obvious reasons. There were bugs in it. Serious bugs. I don't know how many data corruption bugs we saw in corner cases. Not off the bat, but in corner case. When you did a failover and a failback immediately, suddenly you got data corruption in some cases. Really hard to debug, really hard to fix. But we went through that, and I think the entire community went through that in different stages, just to get it stable. Because the one thing we don't want to do is get a system out, and the first thing you do is trash the file system or the data of the customer. That's not a good way to keep a happy customer, right? So we went through a lot of these things. So just remember, when we speak about the different versions, and you see we go from Lustre 2.12.05 to Lustre 2.12 4.3, and then we went to Lustre 2.15. We actually still shipping a version based on the release candidate 4 because we haven't really gotten all the last bits and pieces in there yet, but it is essentially the full release of the version we are shipping today. So when you see the numbers 4.1, 4.4, 6.1, those are the kind of things you need to remember. I couldn't be bothered to put that on every slide. Now, with this hardware, with this technology, what do we actually do when we look at these things? Well, we look at a lot of different tests. Obviously, we do both direct I/O and buffered I/O because some customers actually use direct I/O because they have control of the application. Some are commercial customers, usually do buffered I/O. So this is kind of a mix of those two. We use both fixed time and fixed data. Fixed time, we think, is still the right way to do things because it shows the consistent throughput of an application or a system when you load it fully for 4 to 5 minutes, which is how long we run these tests. But in some cases, you get fixed data requirements, and you always have the problem that you have a tail end because the clients are never equally fast, despite the fact that they are identically from a hardware and software point of view. Some clients will always have a tail that kind of gets your total results down a little bit. But we still do it for consistency. One thing that's important is between every single test, we flush all the caches to make sure that we are in a pristine situation. Because otherwise, you can get a lot of variability over time. We also run these multiple times to make sure that they are always consistent in the results and we don't have too much variability in the results. We also run IOPS. Not that it's really that important on disk systems, but when you're trying to make solutions that goes into specific machine learning and AI type solutions, IOPS is really all the rage. They rarely have throughput that requires the modern systems. I've seen some of the large benchmarks, even with GPU direct storage, that are supposed to get some fantastic numbers, but in real life, when you actually run inference, they're hitting like 10, 15, 20 gigabytes per second, but they may be hitting 1 million IOPS. So it's really a trade-off between those two, so we also need to do that. And then obviously the metadata, which is a challenge as well. As you probably heard, some of the new systems out there have requirements for sustained file crates in the millions of files per second for up to 5 to 10 minutes at a time, which is a big challenge for Lustre file systems today. So we spend a lot of time on that as well. And obviously we do the standard ones like ODB survey, just to make sure the backend works and that self-test, just to make sure that the network is always in a pristine solution. But that's kind of sorry, that's kind of the standard steps we go through. As I mentioned, we run all of these tests, and we do this fully scripted. So that means we throw in one of these sweeps, and it takes almost 2 days to run a full sweep. And then we reformat everything, and then we throw some other data in, and we do it again, and do it again, and do it again, and collect all of these data. So just to give you an idea about what we've been able to do in some of these cases, when you look at an all-flash array, this is 2 OSTs used in parity decluttered array. Tuning parameters has, in some cases, as you can see, gone up by different numbers, but depending on which of these tests we see. It's not uniform by any means. And in this case, specifically when it comes to throughput, this is not a result of Lustre 2.15. Lustre 2.15, when we started with this, had actually had some significant performance decreases. It was actually 20% slower than Lustre 2.12 in the early tests. That wasn't me. So we've seen some interesting things. Now, every time we do one of these, we come up with a new set of tunables. Those tunables are added to the system with its updates. So it's not something anyone does locally. It's all handled by Puppet, so nobody has to go in and set those tunables, because we don't think that users should actually have that control. That doesn't mean that some don't change things, but we try to keep it on a level basis, because not all our customers are Oak Ridge or NERSC or what have you. Or in Europe, I would say CEA and CSS, or Lumi for that matter. Other numbers is a little bit more modest, specifically on the HDD type systems, because there's not really that much headroom you have in those systems. Most of the performances you get out of an HDD system is limited by Gen 3 SAS. Especially when you have 106 drives in an enclosure, you're really limited by how much SAS performance you can get out of these systems. So that's about it. That was one of the things that was interesting. You see, it's modest for most of these things, with the exception of file stats when you do a single MDT. And this is one MDT, MDT0 or MDT1, by the way. They actually produce about the same thing when you run them separately. If you run actually DNE2, which stripe directories, you actually see a certain performance hit that is not necessarily nice all the time. It could be up to 20% in some cases. But the file stats, which essentially is IOPS optimization, that's really due to the new kernel and how it handles the NVMe drives we have in the systems. Same thing with single stream performance. Obviously, there's some significant enhancement in single stream performance on Lustre 215, which is obvious here, with one exception. The buffered writes with fixed time, the buffer writes with fixed time is not affected that well. We're still figuring that one out, because why are the other three showing us, up to 100 or even higher on 100% performance, when that single one doesn't? So there's some weird things going on. And we've spent a lot of time doing that, because we now have customers requiring a minimum of 2 gigabits per second single thread reads or single thread writes, which is sometimes hard to achieve. We also have some other interesting customers that require that all benchmarks should be run with 50% reads and 50% writes at the same time, which is something Lustre is not really good at, unfortunately. At least not when you benchmark it. So that's also some of the challenge we have. Now, I probably have 300 more slides on these enhancements and so on and so forth, but I don't want to bore. I do not want to bore you with too many data, but what I do want to do is show you a couple of things comparing the 3 RDMA type solutions we have today, which is InfiniBand, Ethernet with RoCE, and the KFI or the Slingshot protocol with different things. I did throw Ethernet with TCP in here, and as you can see, TCP is crap. And that's due to a number of things. First of all, these nodes all have 200 gigabit interfaces. And when you run TCP, even if you run it in bonded mode, it will only actually use one of them. So it's really hard to get full performance out of that for writes. Reads, it's not that bad. But what is important here, what I think is really the big message is that regardless if we're using native HDR InfiniBand or 200 gigabit Ethernet with RoCE or KFI, which is also 200 gigabit with built-in RDMA from the libfabrics, we're getting essentially the same results over the board. So hitting about between 58, 59, up to 63, 64 gigabytes per second write on a single array. That's 2 OSTs, 24 drives, and we can do this consistently. The writes are hitting north of 80 gigabytes per second, again, consistently all over the range. And we've done that for quite some time. So those numbers are kind of interesting. Now, what's also interesting, which is something that everybody's been struggling with, it's a well-known fact, is that IOPS is not that great. Take a look at the IOPS. So these are 24 drives, delivering write IOPS in the 85,000 range. Now remember, a single drive can do, about 700,000 write IOPS. on a single drive. But as soon as you apply RAID on top of these, the bottom falls out totally. And that's something we're still struggling with, and a big issue with anything that has to do with RAID. It's not a Lustre issue per se, it is a RAID issue. And you can see the reads are 1.2, 1.3. Now, if you really need good performance on IOPS, you have to go to RAID 10, because the overhead is much less there. I don't have the numbers here, but the write IOPS for RAID 10 is north of 1 million. And read IOPS is north of 2 million. So, if you really need good performance for IOPS, it has to be RAID 10. You cannot do it with parity cluster RAID or RAID 6. Oops. New feature. We did the same thing with the disk systems, and you can see we either are using single JBOD or dual JBODs. Now, dual JBODs is where we peak a little bit on these systems, but you can kind of see from a write performance, we're hitting a good 35 gigabytes per second in most cases. Read is about equivalent on these systems. So, not bad numbers, and again, consistently over the board. Now, if you look at metadata systems and look at different versions of doing that, the results for 32K with or without DOM is pretty much the same as well. So you can kind of take that as a limit. And you kind of see a single MDT can now do about 155,000 write IOPS. Again, these things tend to be CPU frequency based, but we use the same CPU for everything. So the one that really stands out is stats. In 215, stats has really jumped up and are hitting north of 600,000 consistently, which is really good on these systems. That's something we've seen from others as well. But 215 really helped the stats. It hasn't really helped the other ones that much, but it has helped stats a lot. Now, the one thing we haven't talked about here, and I can see James smiling down there, is that all of these things on LDiskFS. I haven't shown you a single data on OpenCFS. And why is that? OpenCFS sucks. Well, from a performance point of view, it is really much slower, especially on IOPS, than LDiskFS is. It has a lot of other values, obviously, but when it comes to performance, it's really hard meeting these numbers with OpenCFS. Now, we've done some changes, for instance, going from NPS 2 to NPS 1 for OpenCFS. That gave us a 30% increase in disk-based IOPS, or IO, not as much on the flash, but we're still trying to optimize that. Every time there's a new release of OpenCFS out, we're trying to implement that as soon as possible, and we are seeing, I would call it, incremental increases in performance as we go to the, I think we're either 214 or 215 at the moment with OpenCFS. But it's still way behind LDiskFS, which is an issue. Again, same thing, comparing in this case, comparing TCP with the other one. So I won't go into detail. I kind of want to get to the final point of lessons learned a little bit. Changing architectures on the server side is really difficult. You have to learn so many new things about the tunables, how to set it up, how to get performance, how to even get multiple I/O cards working in console with each other, which is really, really difficult on these systems. And that's also something that we've been going through a lot. Now, this unfortunately requires frequent work with your developer of the hardware stuff, because the firmware stuff you get, or the firmware versions you get from version 1 or version 2 of these things, is not even, I wouldn't even call it debugging versions. It's barely functioning hardware. And every time we get a new update, again, we get better software, we get better firmware, and we get performance regression that needs to handle some way or another. So it's kind of an iterative process we learned. Now, we also learned that NVMe from one vendor and NVMe from another vendor is not the same thing. We've been using Samsung, we're using Kioxia. Initially, Kioxia was about 15 to 20% faster than Samsung. And none of them could really explain why. It's just what we found. Then we went to Rocky Linux 8.4, and suddenly they were on par. without any other changes. Go figure. But I mean, those are kind of the learning process you go through. Keeping up with Linux enhancements, as I said, we're still on Rocky Linux 6.4. We haven't moved to 8.6. We're not 8.4. We're not moving to 8.6 quite yet, because every time they come up with a new kernel version, you have to start over again, test everything from scratch with every single parameter to figure out how to get it close. Because again, you upgrade, you have a performance hit. And then obviously, newer version of everything will affect the entire ecosystem, right? It's not just a rip and replace and you're back to where you were originally. It's not like replacing a faulty component and you're back to original performance. It is, again, a performance hit usually. So doing these benchmarks, doing it over and over again, is really key to maintaining predictable performance of the systems. So some of these numbers is just the fact that we've been able to tune a lot. 2.15 has been a big boom. Once we got it stable, once we got to figure out that the tunables had to change, and the default values for tunables in the system rarely works that well. There is a slide in the deck that you can look later on. You can see what the default values are and what we actually use, which is usually many times higher than the defaults, because that's the only way we can push these systems. We also found that the difference in RDMA that used to be obvious back in the CentOS 7677 timeframe is essentially gone. We can get the same RDMA results regardless of what fabric we're using, whether it's InfiniBand or Rocky or Ethernet or even KFI nowadays. So that's something that's good. That means it's predictable. TCP still requires a lot of work, but we still believe that with a little bit more work, we can actually get close to where we need to be. But it's really one of those issues that is it worth spending time on it or not? You'd be surprised how many commercial customers are still doing TCP and do not want to do Rocky. I haven't figured out why yet, but there are some, old school defaults that they hardly change. Now the final one is really the important one, and this is my final slide, so don't worry about it. Is can you keep these, or can you actually achieve these data in the field? Can you actually get the same results that you get in the lab on a customer system? Actually, you can if you have full control over everything and know exactly what you're doing. And some of our benchmarkers, who are a lot better than I am on this, are spending their entire time doing exactly that, trying to get things out. But most often, the expectations is higher than the deliverables. That's why we never actually quote full performance to a customer. They never really actually see some of these data outside publications, because these are hero numbers. Reproducible hero numbers, but hero numbers. Because, in the field, things will change. The number of clients will change. The oversubscription of the fabric could be different. The specific version of the clients could be different. I mean, if you're having clients running on something else than a Red Hat version, like an Ubuntu client, for instance, you will see different performance results, and so on and so forth. So we always make sure that we hedge our bets by at least 20% in the field, because it's better to under-commit and over-deliver than the other way around. So that's kind of a long story to say that we're fairly comfortable with doing the benchmark and the numbers we present both publicly and internally. But it is a nightmare trying to keep this up over time. And we have a fantastic benchmark team at HP that obviously split the time between doing customer benchmarks and making sure that all of these different versions work, especially on the big mainframes. So benchmarking is a necessity, but it's boring as hell. Thank you.
Any question?
During benchmark, Do you also remount the file system or format it to get back to the best performance? Or because I know that if you are benchmarking the same file system for days, at some points, you need to at least remount
Right.
to get
So-
those hero numbers.
So one of the things I didn't mention, for instance, on the flash systems, every single run is interrupted with a trim in the between to clean things up. As I was saying, we run a lot of different versions of the OS. So I would say that these benchmark systems are probably reinstalled from scratch once or twice per week. So it's not running the same file system for months at a time, because we know there will be degradation of performance over time as it settles in and you have subtle differences underneath. So we do that as well. But we only have a limited number of systems, and they do get reformatted ever so often because we have to upgrade something. And we'd rather reinstall from scratch and just patch it, because obviously you get better. And then you have the problem of wear and tear. Drives will wear out. You lose a drive in the middle of one of these runs, and you just have to scrap that,
Yes,
replace it,
that's
go
the
back.
worst. When you have like big file system, you cannot rely on the drives. At some point, there is always one drive putting some mess.
Well, let's talk to the Western Digital drives. I mean, they have a mean time between failure of 2 million hours. That means they never fail. There's 33 years mean time between failure. So a drive never fails, right? Well, drives do fail. And then we have problems with cables. And then we have problems with power outages. And then we have, yeah.
Yeah. Any other question?
Yeah, this was too boring, so nobody really.
No, I have one for you. A quick dive question about your CPT configuration. You mentioned that you have an increment from the switching from NPS 4 to NPS 2. I'm wondering if it was not due to this modification. I think it's due to the modification of CPT.
Could be.
It's just a question, because with the RAM CPU, you have 4 CCX and 4 memory controller. And if you spread correctly the CPT on each internal CCX, you will have a full memory bandwidth. It's just a question because...
So basically, we run CTP of 8 on everything we do. We found that has been our most consistent results. But yes, we've mixed around with that as well. We tested all the iterations of that. But CTP of 8 seems to be the most efficient. NPS of 2 for flash, NPS of 4 for disk, and NPS 1 for OpenZFS seems to be the fastest at the moment. But again, we don't trust these numbers consistently, right? We retest it because things will change, and you get a new piece of firmware and things will change, and so on and so forth, right? So repeating, kind of wash, rinse, repeat thingy is something you need to do consistently, and one of the reasons why we spend so much time on it.
Okay, thank you. Any question?
I'm not sure if I have a question, but it's a good comment to that, to this thing with the performance degradation over time on production systems, that you can never, if you do a benchmark 2 years in a system's life, you cannot expect to have the same numbers that you started with at the, when you procure the system.
Right.
And it's, for us as admins, it's sometimes difficult to explain to my management that why do we have poor numbers now? Why isn't this numbers the same as when we bought the system? Well, they don't understand this thing. Well, this file system is 80% full now. It wasn't when we started, stuff like that.
So I agree with that. So I mean, we've actually done those kind of benchmarks as well. What happens with a file system is 80% full, and how much degradation do you really have of performance, and so on and so forth. Because I mean, the right question from a customer is that I want this performance, and I want it at 8% full or 90% full. That means that it sets the bar for what you need to do. Now, one of the things that is hardest for us is the file system slower now because you've added a a lot of data to the system, so it's full or semi-full or whatever. Could it be fragmented, which we also seen at times. But more importantly, when you apply an update and somebody pays a little bit more attention to the file system, and then says, oh, this update made it slower. And how do we prove that it didn't? So initially, a while back, we actually spent about 1% of the outer rims on all drives and created a separate file system on those, what we call benchmark file system, so that you could take the new version, unmount your actual production system, mount that outer sector things, and run the benchmark. And it would be just as good or better than the original ones, because that's essentially an empty file system on the outer rims of disk drives. On flash, it doesn't really matter where it is at, but the same concept applies. There's kind of a set of unused sectors that hasn't been submitted to that much churn. So we could show that the performance was consistent with the initial data. Now, that's become less of an issue lately, because I think the understanding of file system performances have increased significantly in many customers, and maybe not the manager side of things, because they never understand the technology any which way. But at least within the admins around the world, that a file system that's been in use for 6 months, 12 months will be slower because of a lot of features. Now, you could reformat everything, and it will probably regain its original performance. But you rarely do that. So it's really just showing empirical data, and we have a lot of that, and I think every other vendor in the market has that kind of empirical data showing that, over time, the hardware itself doesn't get slower. There may be other factors hitting the media that makes it slower. And one of the biggest challenges that's been lately is, how do you do trim, for instance, on flash? Because trim can really, murder your performance when it's running in the background. If it runs consistently, if it runs opportunistically, or if it just runs on a cron tab every now and then. It's one of those things that's really hard to do. And you can either do that externally, or you can do that for Lustre, which also has some issues as well. So there is a lot of component to this equation that is really hard to put into a simple statement or a simple document, whatever you want to call it. And I don't think there will ever be a good answer to management of this system is now performing at this level, which is expected. If they're good management, they would just listen to you because you know better than they do about what the file system is supposed to do. But we do have that occasionally from different types of customers. And it just, you have to have a discussion, go into details, explain why things are getting slower. But you can never guarantee a file system will work at a certain performance through life. And that's always a discussion you need to have to set the expectations, especially with the disk-based file system, obviously. But even with flash system nowadays, you do need to set that expectation correctly.
Thank you, Torben.
Thank you.
So it's time for break. We will restart at 11:30. Thank you. Guys, time is over. We are going to restart. Our next talk is about snapshot.
So our next speaker is Robert De Roy. He started at IBM NL in 1994, joined IBM UK in 1995, and did his first 1024-node HPC installation in the late 2000s. From 2001, he worked for IBM US in pre-sales as HPC Advanced Technical Support, before returning it to Europe in 2006 to become an HPC architect with IBM's x86 divestiture. Moved to Lenovo in 2015. He's been with LuxProvide for almost 2 years as a senior HPC system engineer for data services, which encompasses, amongst other things, the DDN Lustre solution currently deployed at Meluxina.
Good morning. So first a little bit about LuxProvide. For those that are not aware, LuxProvide is a relative newcomer in the sector. It was set up by the Luxembourg state to procure, host, and run, basically, a European class or supercomputer. This was all started, or the installation was started early 2001. Basically, the system is in operation. We are a member of EuroHPC. On 35% of the system is available through EuroHPC. As I said, the mission is basically that we have to accelerate economic and social progress through supercomputing. We, of course, have a lot of Luxembourg customers. We also, as I said before, are available via EuroHPC, who have a 35% share of the system for European research. So this presentation is about the snapshots, and of course the snapshots need to take place on storage. So Meluxina has 4 Lustre file systems, of which 3 are listed here. So we have a Scratch file system. You can see on the left-hand side, 12 building blocks, 0.6 petabyte usable. This is all DDN storage, all of them. We have a Project Home file system, 10 building blocks, 12 petabyte usable. This is the file system on which we did snapshot testing, and for which the snapshot functionality was requested, basically. And then there is a bunch of backup systems and tape libraries and these kind of things as part of the storage solution. So, lots of snapshots. Clint Eastwood, yes. Luckily not in this order, but we did have some rough spots at the beginning. So the snapshot requirements were pretty basic. To be honest, they were also coming from a GPFS perspective. We were originally expecting to have a GPFS installation. This turned out to be a Lustre proposal instead, that one. So from a snapshot perspective, we were of course looking for creation and deletion. Multiple snapshots needed to be taken to be able to hold a week's worth of data. These snapshots could not have a real noticeable user impact when creating snapshots. And they should have a minimal performance impact when the snapshots are in place on the system. In addition, from a future wish list, basically, we were also looking for an easy way to provide users access to snapshot data, and to allow partial file system snapshots, because at the moment we can only take snapshots of the entire file system. We cannot do a partial snapshots. So the snapshot functionality was requested, or demanded, I could say, by the tender. It was a hard requirement. This was originally committed by the vendor for availability at the tail end of 2020. There were various delays pushing this out into 21. At that point in time, some of the functionality was missing that we were looking for, which pushed things out further. And then when we got to the actual implementation of it, we ran into multiple operational issues with regards to availability of the file system. I will not go into all of the nitty-gritty details here, but it was a long, drawn-out process. Eventually, the system was accepted in July 2020. After co-design and testing, we did deep technical work on partnership with DDN here was essential. That's what the next slide will be about. So after these initial issues, to their credit, DDN prepared an action on the test plan, quite a comprehensive plan. They set up actually two systems in the US. One that was near identical to our system in regards to the MDT, OST counts, and OST size as our Meloxina system. This was for their in-lab development and testing. They also provided us access to this test system via VPN. They provided weekly calls with DDN developers, on WAM Cloud developers, on DDN management. During these testings, multiple issues were found. I think that they created about a dozen internal tickets or something like that for new issues discovered during this time period. The majority of them were found by DDN in their own testing, which is good. We found another couple of issues with our testing on their system. These issues were resolved, at least the critical issues were all resolved. There were still some performance issues which were pushed out to future releases. But all in all, the product was greatly enhanced. Some examples of additional enhancements, basically, the snapshot destroy is now by default asynchronous, so that not the entire user file system freezes when you do a snapshot create. Snapshot destroy is also asynchronous, so it will basically immediately return, and it will be done in the background at lower priority. And there is new snapshot stat functionality to actually see what's going on in the background, something that was completely invisible before this. Not all of that functionality is actually in the current Exascaler releases. Some of them is basically being pushed out to future releases, LDISC FS updates, on these kind of things for the future. From a testing and benchmark methodology, we had some core needs, of course. We needed to ensure the platform stability, something that we had experienced problems with prior. We couldn't have any crashes during the creation, deletion, or mounting of the file systems. We always also needed to make sure, of course, the usability of the file system. We couldn't allow any real interruptions during user access, so home directories, that's part of our problem. The home directories are on this file system, so any freezes of the file system or unavailability of the file system will immediately impact users. No application impact, crashes or corruption, and ensure the performance, so minimal differences in performance with or without a snapshot in place on the system. So from a testing of benchmarks, we did two things. From our perspective, from a Lux Provide perspective, we did synthetic testing using MDTest, and we did application testing using GROMACS, OpenFOAM, and PyTorch. The application testing really wasn't too focused on performance, it was more focused on stability. So for instance, taking pausing the application, on restoring the application afterwards, basically. These kind of functions were done with snapshots in between to make sure that there was no data corruption in place when we restart the application from a checkpoint. This all worked actually fine. We didn't actually experience any problems with that. So even doing a checkpoint restore from a snapshot worked fine. From the MD test, there I fortunately did save some of my data. Some data of the application test unfortunately was not retrievable anymore at this point in time when I was asked to prepare a presentation. So what we did is I did a scripted run of MD test. For this we had 7 nodes available. These were the Fujitsu nodes that were available on the DDN system with Mellanox interconnect, 80 cores per node. So we did so I created a loop, did a snapshot create, ran MD test. After the create at 0, 10, 30, 60, and 120 minute intervals after it to see the performance impact over time of a snapshot create. Would loop over that 5 times, so basically create 5 snapshots. After that, start destroying snapshots and creating new snapshots, as you would probably do in real life, because you would not endlessly be creating snapshots, obviously. So the older snapshot would be deleted, and then we again run the MD test, and that was done in 2 loops. And at the end, we purged the remaining snapshots of the system. So this is to verify the stability and usability and the performance of the snapshot functionality. So based on this, this is some aggregated data. This is not from a single run, actually. This is from a whole bunch of runs where I've taken the median of. So as you can see, the standard deviation, it's quite reasonable. We're seeing in stat operations, we were seeing some degradation in performance. You have to take into account that this actually was running on the 2.14 version of Lustre because of the ARM support, whereby on Mellanox we're actually running on the 2.12 version still. But on the test system from DDN, we could only use 2.14 for the clients. But on the server side, it was 2.12. So the standard deviation or the difference with and without snapshots is really not that great. We're seeing a little bit of a difference in tree removals, which are IOPS, not kilo IOPS. For file and directory, everything is in kilo IOPS here. And once again, this is on the DDN system, actually the smaller one of the DDN system. This is not actually the one that was more or less equivalent to the Mellanox system, because this was done at the tail end and they were reprovisioning the other system at this point in time, these runs. So some interesting tidbits, the performance recovery. So what happens when you take a snapshot, basically? How long does it take for the system to more or less recover from those snapshots? And as you can see, there's a little bit after, so on the left-hand side, you have no snapshots at all. Then the next one is immediately after the snapshot create, we run an MD test. And then we do another one 10 minutes after. As you can see, there's a bit of a dip that goes down, and then the system starts to more or less recover. Some of the operations are more stable than other. As you can see here, the colors may not be too clear, but basically the file stat, as mentioned before, sees the biggest impact in the directory on the file. On file create and also has a little bit of a dip. The tree operations are all over the place, it seems, in all cases. It sees quite an impact after the create, so at 0 minutes, basically, we see quite a dip down from just over 35 to under 20 operations per second. On the tree removal, well, that's is a very difficult one, basically. It seems to be all over the place, even when you even it out over multiple runs, basically. So this is the performance numbers, basically. And that's really the end of what I have to present on this presentation. So that's, I don't know if you want to do questions or you want to present some of the technical part of your side of it.
Okay, okay. Question?
Mm-hmm.
Maybe I missed the information. How many snapshots do you take per day, week? What is the frequency?
In actual operation now, after the deployment of the functionality.
Yeah.
So we're not actually taking regular snapshots at the moment. We're taking occasional snapshots, simply because of some of the prior history. We're still a little bit hesitant of doing continuous snapshots at this point in time, basically. We are looking to start using it in full production. And at that point in time, we're probably looking to create 5 snapshots in a rolling fashion, basically. So we would always have 5 snapshots on the system, once every day, basically. And that way the users could request files to be restored. And this is also mirrored in our requirements our wish list for the future, that we would like to have a user access to these snapshots. Because right now, the way, I don't know if you're familiar with how snapshots work in Lustre, but the snapshots create and then exporting the snapshots to the clients and then mounting it on the client is quite a process. Basically, it's not that easy to automate, especially with the amount of failure situations that can occur with this. That at the moment we would probably do it on demand. So the user would tell us, I would like to restore some files, basically, and we would then do it that way. And then over time we would look to automate this with scripting, basically, to make this available, unless, of course, some additional enhancements are made available by DDN to us, which make it easier, like is available on DPFS with the dot directories.
Okay.
So let me just ask to get it straight. So how you restore files is that you mount the snapshot on a temporary mount point and then you copy the files between the mount points?
Correct. That's indeed how it works. Yes. So on the we first need to run snapshot mount on the storage itself. That creates the export. And then on the client, similar to how you mount any Lustre file system, but instead of you use the snapshot ID basically as the name of the file system, and that's how you mount it on the client on a temporary mount point. And then the user can then restore his files because the access rights are the same. The user can then restore basically the files that he needs to restore from the snapshot. That's correct.
Are the snapshots read-only, I guess? Or
Sorry?
the snapshots are read-only?
The snapshots are read-only, yes. The snapshots cannot be written to.
I have a last question. Have you evaluated the impact on the OST part?
The impact on the backend, on the OSTs?
Yeah.
Well, the impact on the OSTs doesn't seem to be very high. It seems to be mainly metadata related. We did not really do many tests on the OST performance, but we didn't really notice too much of an impact on it. Okay. Like I said, it seemed to be mainly metadata operations. That's why we were looking at IOR performance.
Exactly. Okay, thank you.
Do I have to go to a different presentation?
It's yours.
Hi, so I'll be talking about the sort of the more technical aspects of how Snapshots was implemented. So we did look at a number of different options for how we might implement Snapshots in Lustre. And I mean, DDN, mostly uses LDiskFS for their deployments. I mean, we did look at ZFS, and so, ZFS has integrated snapshots, that's great. ZFS has other features, as Torben had mentioned. One of the issues with ZFS is the performance, right? And in particular, you know, we had worked at Intel for quite a number of years to improve ZFS performance, metadata, and things like that, but it's still lagging. And in particular for high IOPS usage with Flash, you really notice a significant difference, and so we didn't wanted to change over to ZFS. There was also a separate project, Fujitsu, that had DL Snap, and so, you know, that had a benefit that it was in use on the K computer. One of the negative issues there, several negative issues. One is that the code was very old. It was originally developed for Lustre 1.8 and you know, hadn't seen very much update, and they were not very interested in doing any updates, even though the code was eventually made available to the community. But the other technical issue is that the DL Snap requires that every single file that's being snapshotted is processed. And so if you're doing a snapshot on a file system that has, you know, 1 billion files, it's more like a small directory kind of functionality rather than a whole file system functionality. And so we didn't think that that was going to be very practical. And so there was another set of patches that were submitted into upstream ext4 from a company named Cetera. And those provided whole file system snapshots. There was already E2FS progs and E2FS CK support for it. There had been some work done to reserve, you know, metadata fields in the upstream, you know, kernel for those snapshots. And because it's LDiskFS, you know, ext4 based, you know, this provides a way for existing DDN systems to use the snapshot functionality. But, you know, again, while the patches were against newer versions of ext4, they still did need some updates. And the other area that ended up needing quite a bit of work was handling very large file systems. I mean, originally the Cetera patches were only for file systems up to 16 terabytes, and so that's not very practical for Lustre. But it looked like the best solution at the time, and so we based the snapshot work on that. And essentially, the way that the snapshots are implemented is that inside LDiskFS, essentially a snapshot is a virtual image of the file system. And I mean, we wanted snapshots at the LDiskFS level partly to match how ZFS was implemented, so we can use the same commands, we can you know, have consistency between the different backends, but the snapshots, each target takes a snapshot of the local disk file system. So for each OST and each MDT, we get an independent snapshot, and you know, they can be either, you know, taken all at one time with a barrier, which essentially blocks all client I/O to the file system and all metadata operations. And while that's, you know, seems appealing, you know, one of the issues is that it has a performance impact to the running application. And it turns out that that's, you know, while it seems like, oh, I want an atomic snapshot, that's great. It turns out that it's actually not, you know, as great as you might think, because even if you're taking an instantaneous snapshot, you still don't know the state of the applications at that time, right? So if applications are writing to the file system, you know, they might be right in the middle of a syscall and have lots of dirty cache. And even if we flush the cache, they might be, you know, writing half of a file. So you can't really expect that snapshots being taken, you know, while applications are running are going to get you consistent data. And so Lustre itself, because it's an aggregation of independent file systems, we can already handle the fact that there might be some inconsistencies between the MDTs and the OSTs and things like that. So the snapshots are not taken essentially atomically, and we just run them asynchronously in the background. So at the file system level, essentially each snapshot is a full virtual image of the entire file system. And so when the snapshot is created, you get an empty file system. It has a copy of the super block and things like that, and we export the snapshot images as loopback files to user space, and then we can mount them using regular, Lustre tools to mount the file system image. This works for both Lustre mounting and LDiscFS mounting, and we can do things like running E2FSCK against the snapshot images to make sure that the snapshot itself was taken correctly. One thing we did have to do is implement a file format that supports larger than 16 terabyte files. And because of the nature of how snapshots are created as random, IOP block IO, because you don't know what blocks are being modified, we ended up going with an indirect file format rather than extents. And so that's actually a 5-level indirect tree. We call it 5ind. But that format is only used for snapshot files. And so even though it's not supported in upstream ext4, when you delete the snapshots, those files go away. And so we can always, pick a different format in the future if we need to. And the code itself ended up being about 10,000 lines in LDiscFS for the snapshots and about 5,000 lines for the 5ind large file format. But a lot of that is boilerplate. It just means add in, instead of indirect, double indirect, triple indirect, quad indirect, 5 indirect. It's a lot of boilerplate code, so even though it's a lot of lines, it's not as much complexity as you think. And when you're modifying, after you've created a snapshot, when you're modifying the files, you have this initially sparse file, and if you make a modification, say you're modifying an inode, it will take a copy of that block and write it into the snapshot file, because in LDiscFS, the metadata locations are fixed, and so we have to write a copy into the virtual location of the snapshot file at the right offset. For data blocks, we instead of copy on write, we have move on write. So you don't actually make a copy of the data blocks, which is the biggest volume of data. You move the pointers for those data blocks to the virtual inode inside the snapshot file, and then you overwrite a new set of blocks in the regular file system. And that's fine because all file blocks in a file system, when they're being modified, they're being wholly overwritten anyways, so it avoids an extra data copy and performance impact. Because even with if you're writing 1 byte of data to a file, the Lustre client is going to do a 4K read, modify, write. And so we'll always get at least block size IOs into the snapshot. And we have to exclude blocks that are part of the snapshots themselves, so we don't recurse and make the transactions big. On the read side, if there's holes in a snapshot, it will read through to the next older snapshot or to the main file system, so that we don't have to make copies of all the data and metadata in the snapshot files. So this was already covered a lot. We did do testing, up file systems up to 500 terabytes, and one of the things that we noticed is the snapshot creation for very large file systems can take some time, but we did improve the performance of that significantly over time. Initially we had been doing the development on smaller file systems and with NVMe, and that worked fine, but the very large hundreds of terabytes OSTs did require some extra work to optimize the snapshots. And I think this is the last slide here. So we did originally develop and test it on EL 7.9, which is the current server kernel for Exascaler. Most of the changes are in LDiscFS. We did have some user tool work. And what else? FSCK. You can run FSCK on the snapshots. We can't actually fix a snapshot if it were appear to be corrupt, but you can delete them. This is like deleting a regular file. So it's actually not very complicated to delete snapshots. And E2FSCK -X we'll delete all of the snapshots and then, you know, clear up the block references and things like that. So it's relatively low risk from that side if there's a problem with the snapshots. And we're just in the process of porting this to EL 8.6 kernels. Actually, and I think that's it.
Thank you. Any questions?
Does the snapshotting affect quota after copy on write effects?
Well, we did have issues with the quotas because it was counting that as extra space against the users. But because it's a copy, if a user deletes their file, for instance, but there's a copy in the snapshot, they're not charged for the copy that's in the snapshot, right? As you'd expect. Yeah, it's only the data in the main file system that's counted.
I understand this is a exascaler addition. Do you have any plan to release those changes open source?
We're currently, you know, just updating it. It's against an older kernel, and I mean, RHEL EL 7.9 is not even supported in, you know, 2.15. So it does need some updates. You know, there's some management questions there too, but you know, eventually, yes, that's one of our goals, just to reduce the maintenance and things.
Thanks.
I understand that taking a snapshot during the workload does not guarantee any coherency from an application point of view.
Yeah.
But I think the barrier feature try to have something coherent between MDT and OSTs, especially on the file system metadata. So I feel like it's still useful to have that, like to guarantee in-flight operation from the MDT to the OSTs, these kind of things to be coherent.
Yes and no. I mean, you know, Lustre itself can handle a lot of the inconsistency. I mean, the most error that you would see, it's not like, let's say, GPFS, where the blocks have to be consistent across all of the storage, right? With Lustre, because each file system is independent, I mean, the snapshots are still, you know, atomic on the per file system level. And so the most that you would see is in some cases, let's say if you, you know, we're deleting a file and the OST snapshot finished before the MDT snapshot, you might get like enoent when you're trying to access a file, right? But it's not going to cause problems for Lustre. Right, so but those files, I mean, if they're right in the middle of being deleted when you create the snapshot, it's kind of, you know, it's a race condition on whether you take the snapshot a millisecond before you delete it or a millisecond after, right?
But with barrier, you avoid this kind of case.
Yes, but you know, even taking the barrier, I mean, you're quiescing, if it's a large cluster, you're quiescing the I/O, you know, across 1,000 nodes. You know, that might take, you know, minutes to flush all of the data out, right? And so it can be disruptive to the application.
Okay, thank you.
I have just a complementary question about this. Are you going to support the LFCK on the snapshot to gain about coherency?
No. Because you can't modify, the snapshots are read-only, so you couldn't fix it anyway.
Okay. Any other question? Okay. Myself again. I have seen that you rely on a kernel loopback driver for the copy of the image.
Yeah.
You are supporting the EL7 kernel, and you know that the loopback driver has some significant stat performance, in fact. Have you seen this? Because if you go through the loopback driver, you will have some poor performance.
Yeah, I mean, we did look at patching the loopback driver in EL7. I mean, it's better in newer kernels, but it's also different structure. I mean, we don't actually change the loopback driver. We're just using it to access the virtual, file inside the snapshot. And actually, one thing that I didn't put in my presentation was about the question about how easy or hard it is to access a snapshot. That's one of the areas of development, so that you can auto-mount the snapshots on the clients and things like that. And I mean, we'll actually try to make it more transparent so that you don't see them as separate file systems on the client, but that's a lot more work, getting the base functionality, and newer kernels have better support for loop and things.
Okay.
All right.
Thank you.
So we are ready for our last speaker of this morning, Marc Bonnet from Western Digital.
So Marc Bonnet is a technologist field application engineer at Western Digital EMEA. He's working and collaborating with strategic customers who architect, develop, and build new storage solutions for their data centers or enterprise platforms. He's been working in the disk drive and storage industry for more than 25 years. And he owns a master's degree in physics and engineering degree in microelectronics.
Okay, good morning, everyone. I'm happy to be here with you for my first LAD. Thank you to Gael and CEA for the invitation. So today I'm going to talk about how to improve a parallel file system like Lustre using the NVMe over Fabric solution, storage solution. So I want to point out the fact that I'm not, the credit for this presentation and for the POC belongs to Jonathan Flynn, sorry, who is part of our field application engineering for platforms based in Colorado Springs. So I'm sure you are all familiar with this traditional parallel file system architecture with the management server, the management target, the metadata servers, the MDT, and so on. So basically, the one issue you are well aware is in case of one OSS failure with this active-active failover architecture, basically you have one server taking care of the workload for both OSTs. Okay, so this induce reduced OST performance, or you need to scale your server performance to take care of this situation. So basically, the solution is not cost optimized because it needs to be the computer resources and the network resources need to be sized to face this type of situation. Okay, now let's look at the storage enclosure evolution and the challenges, okay? So this is a traditional JBOD product using a SAS dual port drive. If you want to improve the performance of your parallel file system, then you can move to same type of enclosure with SAS SSDs. But basically same architecture, same topology. Now we have this new, or let's say, this very high-performing NVMe devices coming with a dual port as well. But this is really a completely different device. It is connected to the very high-performing bus, the PCIe bus, Gen 3, Gen 4, soon Gen 5. So how can we handle and get the most performance out of this type of device in a parallel file system. The current approaches are basically could be to use a single OSS with a RAID layer, and then you have basically RAID protection with either software RAID or hardware RAID. But in this, there is very limited, benefit with this solution. Basically, you have no protection against the server failure. Okay. Also, we have experienced that with traditional software hardware RAID architecture, you can get limited performance. Now you have also the possibility to use a 2U with a 2U server with dual node with 24 NVMe device. You can create this time 2 RAID groups, RAID 5. So this is a much better solution from a failure standpoint. But again, with that solution, you have a limited number of SSD to address. Basically, with 2 servers, you have only 12 SSDs. And you have also quite an issue with the number of devices to have a pertinent RAID level. Meaning, if you want to have a traditional 8+1 or 8+2 base 2 OST RAID layout, basically you are going to end up with using only 20 devices out of the 24. So not really an optimized solution. Okay, this is the 2U HA server that we used to sell from Western Digital, but we moved to a new solution now. So this new solution is basically a 2U24 NVMe JBUF, okay, enabling a standard NVMe PCI SSDs that can be shared through an external enclosure through the network. Okay, the enclosure is a 2U with also 24 devices, very similar to the SAS enclosure we saw earlier. But this is simply a JBUF. There is nothing to manage the RAID and so on. In terms of networking, this solution, which is on our portfolio since 2 years now, is coming either with it's coming with 2 I/O modules to get the high availability support, and you can get either 1 Ethernet port, 100 gigabit per IOM, or 3 ports for a total of either 2 or 6 Ethernet ports. So maximum bandwidth of this enclosure is 600 gigabit per enclosure. Currently, with the platform we are selling, it's only ROCE V2, but happy to tell you that soon we will release the TCP. We will support TCP, which is, let's say, somewhat easier and natural transition for our customer. And of course, we have a BMC for management, and the enclosure is coming with our own API to manage the enclosure components and to manage the storage. By the way, the product is called OpenFlex. This is a new brand name at Western Digital because effectively NVMe over Fabric provides a lot of flexibility compared to previous architecture. So, and this is also an open architecture. So now, as I said earlier, we observed with NVMe devices some limitation with RAID layout. So typically, parity calculation are done on the kernel space, which is not very efficient. So to make the solution really efficient, we need some basically hardware-based parity calculation. And we have looked at different options. Okay, one option is to use CPU extension from the x86, AVX, AVX2, which are available. There is other solution to use a GPU. There is on the market a solution named GRED, which offers this type of possibility. And similarly, you have a solution, you could we imagine a solution with a FPGA, okay, for parity calculation. And this solution, I mean, are clearly, a key element to boost the performance and get the most of the performance from your NVMe devices. These are the solution, and now this is a concrete example we have tested internally at Western Digital with a solution named Radix. Okay, so this is a software solution. Radix is used to be a Russian-based company. I think that they have moved to Switzerland now, but the solution is still available. So these are the details of the configuration we have tested. So we took 8 NVMe drive. In that example, we only use 2 PCIe lanes. Okay, this is and they were Gen 3. So we compare the raw performance with MDM, with the 8 drive, RAID 5, and then with Radix. And we did 2 benchmarks. One was a sequential write with 128K, and then the random read and write with 4K byte blocks. Okay, you can see for reads, no real benefit out of this Radix solution, but for write it's obvious, and we have observed on random IOs for write. Basically, the performance is by 10 improved, and by 6 for sequential write. Here, just something important. Of course, this performance is quite dependent from the stripe size. Okay, I mean, if your block size is 128K and you use stripe of 16K with 8 drive, physical 8 drive, then you end up with only 7 drive to write, and you have a read modified write, and the performance is impacted. So the 7+1 solution for that type of example is not optimum. So you better to use 9 drive. So you need to watch this type of setup. So let's look at the traditional HA server performance and what you can get out of the 2U24 HA server. Basically, you have 24 devices, and you have 2 nodes, so OSS1 and OSS2. You can create using 2 namespaces per device. You can create 6 OST. Okay, so by the way, our devices and NVMe devices all support multiple namespaces, and you can create up to 128 namespaces, but commonly less namespaces are used. So in this example, you have basically 2 OSS, 6 OST, 3 OST per OSS, and you have each OSS is, of course, active and passive. Active, so OSS1 is active on OST 1, 2, and 3, and passive on OST 4, 5, and 6. Okay, we found difficult to design with this type of architecture the solution to in failover condition, because basically if OSS 1 is going down, you only have OSS 2, which can take care of the OST of the OSS 1. Also, in such a condition, this is difficult to get the full performance of the solution unless you have basically provision your performance on CPU, on network for the server to take care of this situation. So basically, you need to design and to size your resources to take care of the failover situation, to plan for a failure of one node. Also, performance needs to be to have 2 times 100 gigabit to support the performance in read. Okay, and as mentioned earlier, without any solution hardware accelerated read parity calculation, you end up with a very poor performance with MDM. Okay, so yeah, the challenge are basically limited flexibility, very limited flexibility in case of failover situation, and as said before, the way to create OST is might not be optimum to get the maximum performance, and you may end up with unused device, like I said before. In this example, we with these two nodes with the optimum read layout, you have only 4 OSTs, and you end up with 4 spare devices. Okay, from a rack diagram standpoint, with this type of solution, in this example with 10 dual node OSS enclosure, okay, we have 2 OSS per enclosure, 6 OST. So at the rack level with 10, you have 60 OST, and the big point is basically you end up with power consumption which is very significant of 17 kilowatts. Okay, so you need to basically to be ready to cope with this type of power. Okay, and the key point also is you spend 50% of your resources you need to basically reserve and plan 50% of your resources to plan for a failover scenarios. Now comes the NVMe over Fabric architecture. Okay, so the principle of this architecture is this is any to any topology, meaning on this architecture we have worked on. We are proposing to use, for example, one device from multiple enclosure. So we can stripe the red layout with one device per enclosure, and you have then a very flexible layout like 4+1 or 8+1 or 8+2 and so on. So very flexible. The other key point is each OSS can can address any OST. A very flexible solution because everything is assignable or role assignable through the fabric. Okay, you don't need to plan for 50% additional compute and network resources because of this architecture. So. In this example, you can see you have an idle OSS 3, which is ready to become active as soon as one node will go down. In fact, this extra OSS in idle mode is not necessarily required. Okay, you can plan additional resources on on your OSS, let's say add, for instance, 10% additional compute and network resources to each OSS, and you don't need to have an extra OSS. Okay. And of course, with this solution, we will use the hardware accelerated RED solution to take the full benefit of the NVMe performance. So the benefit of this solution is, of course, the resiliences. Any SSD, any server, any enclosure, any network link can fail. Okay. The flexibility with the RED. Okay, we are not like with the 2U24 dual node server, limited in terms of flexibility with the RED, losing, I mean, having up to 4 devices unused, so this is very efficient in terms of cost. Yes, instead of having 50% of additional OST server, you only have a limited cost needed to plan for this with this architecture. And you have, and this is quite important, you have a full flexibility to select your OSS server. This could be a 1U server without any NVMe. So a great level of flexibility to choose your server and assign the role you want to each of these server. In the POC we did, we selected all the same server to assign different role. And the performance, of course, the performance is on right is improved, of course, with the accelerated hardware accelerated solution, but also because we have the free flexibility to do basically a RED layout which will max the performance. So just to finish, because I understand that I will only cover 50% of my presentation, but you will get the detail on the backup slide. If we look at the performance here, you can see with a raw solution, raw performance with 8 drive, the OST is 7.55 gigabyte per second. You have 2 OST per OSS. And at the OSS level, you have twice, so about 15 gigabyte. With the MDM, basically, you only, without any acceleration, you only end up with 11% for write bandwidth. With the accelerated RED, you jump to 65%. Then, if you do a better layout in terms of RED, you jump to 93%, okay? And again, with having very limited resource provision to face a failover situation. So we believe this is a great solution to prepare the new generation of parallel file system. Thank you very much.
Thank you. We have just time for one question. Nobody? I think they're hungry.
Okay, anyway, don't hesitate to send me an email. My email address is very simple, mark.bonnet, B-O-N-N-E-T, @wdc.com. I'll be very happy to answer or to get help from my colleagues to answer any question you may have. Thank you.
Thank you. So it's time to lunch. Same place as yesterday. and the return will be at 2. Have a good lunch.